My name is Jamaica Marshall, and I am so pleased to serve as the Shadow the Scientist Coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. In this session, we have the privilege of shadowing astronomer Mark Everett, who will be observing at the WIYN 3.5-meter telescope on Kitt Peak in Arizona using the NESSI Exoplanet Stellar Speckle Imager to acquire and gather data on stars. The Kitt Peak National Observatory is located on Kitt Peak of the Quinlan Mountains in the Arizona Sonoran Desert and is one of the largest gatherings of astronomical instruments in the Northern Hemisphere. The WIYN telescope is owned and operated by the WIYN Consortium, which consists of the University of Wisconsin, Indiana University, NSF's NORLab, Pennsylvania State University, the University of California at Irvine, and Purdue University. The instrument being used for this session is a speckle imager. Speckle imaging is a high-resolution astronomical imaging technique that uses very short exposure times to freeze out the effects of atmospheric turbulence. This effectively eliminates the distortions caused by our Earth's atmosphere to enable angular resolutions equal to the theoretical best possible for a given telescope, thereby delivering space-based resolution from the ground. Now, without further ado, let's meet our guide on this stellar journey, Mark Everett. Welcome, Mark.
Thank you very much, Jamaica, for the great introduction. I think that you've almost knocked off all the topics I wanted to talk about already, but hopefully I can come up with a few things. And welcome everyone to our Zoom session here at Kitt Peak. I see we're getting a few more people coming in now. But I want to kind of tell you the news so far, and I'm going to start sharing my screen here. What's going on the mountain. And unfortunately, it's not, I believe you can see it now, the share screen. Unfortunately, we don't have good news. What I'm showing right here is the current radar, and I will just update it. We have storms all around Kitt Peak right now. This is a radar image of southern Arizona. And Kitt Peak is right about here. And you can see that the storms are almost overhead right now. And what that means is that we don't anticipate actually opening up the telescope anytime soon at all. So the plan I'm going to talk about the plan that was supposed to happen tonight and hopefully have some time to share. Okay, we actually have a little radio weather warning came up actually here at the control room. But what I'm going to do is I prepared some slides just in case we had one of these rainy nights. And I want to show those to you. And of course, I very much welcome questions from the audience here. So I believe that Jamaica has allowed everyone to potentially unmute themselves. So that's probably the best way to get my attention, although maybe Jamaica can also monitor the chat. If that's the case, I think yes, Jamaica may also monitor the chat and see if there are questions that pop up there, because I will probably miss it. It's hard to keep track of everything.
Mark,
okay.
I'd be very, very happy to monitor the chat. And I will say to everyone who's with us, if you would please raise your virtual hand, then it'll be easier. You'll pop to the top of the window and Mark can easily see that you have a question. And if for some reason he doesn't see you and I don't see your hand, please just pop it in the chat. And I will make sure that Mark sees it. And Mark, if I may, before we continue, I'd like to also recognize not only our amazing regular guests who are here with us, which again, I mentioned before, Rob, Yael, and Vonnie, and some new faces, Eddie, Irene, and Phil. But we also have with us an upcoming Shadow the Scientist host. This is Nick Scott from the Chara Array. Nick, would you let me make you co-host Nick. Nick, if you'd like to pop on real quick and say hello and give us a quick introduction, we'd love to hear from you.
Sure. Hey, Jamika. Hey, Mark. Good to see you both. Yeah, I'm at the Chara Array now and going to be hosting some Shadow the Scientists talks there. And then I'm quite familiar with the Kitt Peak and NESSI. Yeah, I was hoping to see it run, but weather is the weather. So yeah, good to see it. Thanks for doing this, Mark.
Yeah, thanks for joining us, Nick. It's good to see you.
Yeah.
I just want to start out by saying that the person who designed the NESSI instrument, what we're going to be talking about tonight, was actually Nick. So he's very familiar with NESSI. So I've known Nick for quite a while.
Yeah.
And it's great to see you here. So
yeah. Well, thanks for keeping it running. Mark's been using NESSI since it was built and keeping it running and taking good data. So it's the best of all worlds for instrumentation of design it, put it on the telescope, and then I haven't had to deal with anything from it since. So thanks for all the stuff you do on that, Mark.
Yeah, well, it's a well-built instrument. That's why it's not really giving us any trouble. It's when you're dealing with a lot of instruments, like WIYN has a lot of different instruments. It's very great to have at least one of them that's always working. You can just kind of turn it on and it goes. And that instrument is NESSI. So
yeah,
thanks for your great work, Nick.
Yeah. All right, thanks. I'll happy to help with any questions if everyone have it. But otherwise, I'll let you run the show, Mark.
All right. So I've actually prepared some slides. Give you a little slideshow tonight to start. I hope everyone can see this. And maybe I'm not sure what it looks like when I'm sharing, whether you see the window with the people in it in the corner or not. But hopefully that's moved out of the way more or less now.
That's correct. Yeah, we just see the map.
Okay, great. So I want to sort of start out by situating where we are, where I'm broadcasting, where I'm sitting right now. So I'm here at Kitt Peak National Observatory. This is right here in southern Arizona. The nearest good-sized city is Tucson, and we're kind of to the southwest of that. On a mountain about almost 7,000 feet in elevation here. So, and here's an aerial photo taken of Kitt Peak at one time, not too terribly long ago. So you can see there are a bunch of different telescope domes on this mountain. And the one where we are at WIYN is right here. It's kind of on the precipice here on the south end of the mountain. 3.5 meter telescope, as Jamika told you. And we have a number of other telescopes on the mountain. This is the 4 meter in telescope in distance there. That's the other telescope of comparable size. There's also an relatively old 2 meter telescope here. This is an old solar telescope called the McMath Solar Telescope, which is no longer actually being used. It's being turned into a visitor center there on one part of the mountain. And you can see a bunch of other telescopes on the mountain. So Kitt Peak overall is overseen by what we call Noir Lab now. Noir Lab kind of operates the machinery and things on the top of the mountain. And then there are a bunch of other telescopes here that are operated by mostly different universities. They have a kind of footprint on the mountain, and they pay in a little bit and they keep their telescope on the mountain. This is also on the land of the Tohono O'odham Nation. So we're very privileged to be up here observing from this summit, Kitt Peak. So these are a couple of pictures closer in on the WIYN telescope. You can see on the left the WIYN building. And I'm actually here in the control room, which is in this, under this roof here, this part of the building here. And you can see over here the WIYN dome, which is, the telescope is upstairs from where I'm sitting here. It's up a couple of flights of stairs, a couple of floors up here, open in this particular image. And here's a picture actually of the telescope. Looking down here in the primary mirror, that's 3.5 meter diameter telescope. This is a reflecting telescope. We often call it well, there are different places to put the instruments on it. What we often do is put the instruments on the side of the telescope, so that that is called the Naismith focus of the telescope, where the light will come down, hit the primary, it bounces up to the secondary mirror, which is up here. It comes down again, and it hits a flat mirror, the tertiary third mirror, and that will direct the light to one side or to the other, where it can reach these instruments on the side at the Naismith focus. And that's where we actually put NESSI. NESSI is not actually pictured in this particular photo. And this is the control room at WIYN. This is where I'm actually seated right now. I'm broadcasting. I took this control room photo, which spans about 180 degrees. So it's a little bit strange looking. I took it just this afternoon. Which you can see, this is a very typical control room for a telescope like this. On this side of the room, we have a bunch of computers and monitors. These are used by people operating the instruments on the telescope. And then on this side of the control room is where the OA, or observing assistant, sits and controls the telescope. They're operating the telescope, they're watching the weather, monitoring various systems like that, so that the observers on this side can kind of concentrate on what's happening with their instrument. And over on the left, this door is a door that heads out to the ground floor underneath the telescope. And you would take a flight of stairs up to 2 floors to the telescope level. And then the door on the right leads out towards the instrument lab and a computer area where we can open up instruments and work on them in there. So I don't see any questions yet, but you can ask if you have that. So Jamaica said already that WIYN is a 3.5 meter telescope and is operated by the United States National Science Foundation National Optical Infrared Astronomy Research Laboratory. So that's what we call NORLAB. So that's just one of the partners at WIYN, and these partners are always changing. So this is the current list with NORLAB, Indiana University, the University of Wisconsin, Purdue, Penn State, and Princeton. So these partners all get a share of the telescope and use a share of the time on the telescope. And what we're doing tonight, or hopefully we might actually get to do late at night, is to do Q observing using NESSI. We'll talk about NESSI. It's a Speckle imaging camera. And when I say Q observing, I'm talking about a certain type of observing where we're observing for a number of different programs. Different principal investigators have programs within a queue. And when I'm operating the queue, I can switch back and forth between these different programs and observe different projects or different targets, depending on the time of night and the conditions, and get, it's an efficient way to use telescope time, essentially. All of these different programs, they don't have to send someone to the telescope to to do a particular project. They can just send in instructions to me and I carry out the observations for them. That's one of my jobs actually at NOIR. And the goal of the observing tonight is to get the Speckle imaging data for 5 different programs in the queue. So what we're going to do is ideally get high resolution images of particular target stars and their surroundings. We're actually looking at only a very tiny patch of the sky where we do this high resolution imaging. And the target stars we have are going to also be relatively bright stars and nearby stars. If you're familiar with the magnitude scale, we might typically observe stars from magnitudes 8 to 14 or so, like that. And we typically look at nearby stars because if they're nearby, our high resolution images are looking close in to the star, just because of the geometrical accessibility of those nearby stars. So you might ask, why are high resolution images of stars useful or interesting? As I said, we usually look at one star. And why is it interesting to look at a star? Because these stars usually appear as an unresolved point of light. And the main reason is that because many stars are double or triple or quadruple stars or even higher order stars. And these could be a true binary star where we're looking from the left side of the screen and viewing a star, two stars, let's say, that's in a binary, they're orbiting one another. So they're physically they're gravitationally bound together and orbiting one another. So that would mean they're close together in the sky. Or we could look at an optical double where the stars just happen to lie close together in the sky, but are only along a certain line of sight, one in the foreground and one in the background. So we would look for both of these cases. And why is it important? Why is it important to look at single or multiple stars? There are several different cases. One of them is that single stars are simple, while double stars can be confusing. That's because if we know something about a star, if we know its temperature, its mass, things like that, we know almost everything about it and we can interpret the data pretty well. But if it's double and we don't really know it, the light from the two stars is combined together, and that's a much more confusing case. And I will go into that in a little bit more detail. So we have different programs. Some of the NESSI programs want to select the single stars because they're easy to understand. They're good things to study. Then they have other NESSI programs where they want to find the binary stars. They may have known binary stars and they want to study them, or they're looking for triple stars. Because these things are also interesting in their own right. They're pretty common, actually. Other programs may already have data on an interesting star, but they don't yet know whether the light they're looking at comes from a single star or two stars closely together in space whose light is commingled and getting into their instrument. And in order to interpret the data correctly, they need to know whether they're looking at a single star, receiving light from a single star, or from, say, two stars. And NESSI's main goal has been, and NESSI has operated since 2016, its main goal has been usually the characterization of exoplanet host stars, so stars with known planets orbiting them. And the reason you want to characterize these stars, you want to know something about their basic properties, like how massive the star is, how large the star is, things like that, is because when you're studying these stars in the context of exoplanets, you're usually looking at the star's light. To understand the properties of the planet, you need to know how the planet is affecting the star's light, which is what you're actually viewing. And I'll give you an example of that later on. So here at WIYN, we're a ground-based telescope, and that has some limitations, various limitations. And one of the main ones is that when you look up at a star or a galaxy or anything else through the atmosphere, you're looking through a turbulent atmosphere, which is a mixture of different cells of lower density or slightly higher density air, slightly hotter or warmer or slightly cooler air. And as the light is passing through this turbulent mixture of different cells of the air, it's being refracted as it's passing from a low density through high density cells of air. And when light gets refracted, it's slightly changed in direction. And my best analogy I could think of would be what happens on the floor of a pond, of the bottom of a pond, or the bottom of a swimming pool, or the bottom of the ocean if it's well illuminated by the sun. And you see this I'm sure you've seen this pattern, these sorts of patterns before, as the waves on the surface of the water are actually refracting light as the light passes through that surface. The light is hitting the surface and those waves on the surface at different angles, and it's being refracted in different directions. But by the time it hits the bottom of the pond, and you can see the familiar kind of dark patches and light areas on this pattern here. So you can kind of imagine if you were a small fish or just a human eye that's near the bottom of this pond, and these waves are passing over you, you are going to be either in a dark area or a light area at any given time. When you're in the light area, you're seeing the sun as a brighter object. When you're in a dark area, you're going to see the sun as a darker object. And the sun is going to, as the waves pass over you, you're going to be seeing a lighter or darker object. And that's essentially what you're doing when you're outside looking at a star and you see the star twinkle, as it says, or this scintillation effect. It's the star is becoming rapidly darker or brighter as you look at it. Now, with a larger telescope, like a 3.5 meter telescope, as we have with WIYN, we actually are capturing a whole bunch of different light patches and dark patches if we put it at the bottom of the pond like this. So the effect is a little bit different. When the light hits the telescope primary mirror, parts of the primary mirror are illuminated by light that is coming from slightly different directions, even if that light had originally been parallel as it's hitting the top of the atmosphere. By the time it gets to a telescope on the ground, parts of the mirror are being hit by light which is slightly out of parallel with other parts of the mirror. And when you focus that, as a telescope focuses the light of a point like a star, you actually don't get a point of light in your focus, but you actually get a set of speckles. The light is broken up into a set of speckles, and I'll show you what that looks like in a moment. And another thing about those speckles is that they vary very rapidly as the atmosphere moves across this telescope's view. Now I'm going to try to see if I can. I might have to stop sharing here. I'm not sure how the best way to operate this. Am I sharing?
No.
Okay.
You stop sharing, but you can reshare whenever you get
Right.
a chance to. And we do have a couple of questions in the chat whenever you're ready for those.
Right. Okay. So one of the looks like the first question: how is telescope allocated among the partners? Well, different partners want to buy in. They have a certain amount of money they're willing to spend, a certain share they want to buy at the telescope. And essentially, the telescope time is allocated proportional to how much money they're putting into the pot, which is the operating funds for the telescope. And in terms of what I do with the queue when I'm using NESSI, that is determined by time allocation committees. So the people who want to do a program will send in a proposal for the program. They'll ask for a certain amount of time that's needed, estimated to do their program. They'll either get that time, they might get a slightly adjusted time, or they might not be awarded that time. So what I would do when I'm deciding how much time to spend on one program versus another is to look at how big of a share they have of among all the different Q programs. Okay, and second question, is the observing assistant the same as the telescope operator? Essentially, that's yes. It's just a different name that's used at different observatories. Okay, and so third question, how you're able to identify the molecular signatures of things like carbon dioxide, water, and methane in the spectrum when observing exoplanets. So that's a good question. Basically, when we're observing here, we're not actually observing the exoplanets, but only the exoplanet stars, the star around which these exoplanets are orbiting. So we can't do this with NESSI necessarily well, but if you want to know something about the composition of the star, you would use another instrument like a spectrograph. You could get the spectrum of the star and measure things like the temperature, get the basic properties of the star, like the temperature of the atmosphere of the star, and then based on that, look at the strengths of different lines that are produced by these things like the carbon dioxide, possibly, but carbon monoxide, other constituents in the atmosphere of the star. Do you catch exoplanet transits? It's another good question. Yes, we don't do a lot of that with Speckle because we don't typically measure the brightness of the star that precisely, so that it's not necessarily easy to use Speckle simultaneously while looking at a transit or a star that's being transited. But we could use NESSI as a more traditional imager and just take image after image after image and look at the brightness of a star as it's undergoing a transit. So I think I forgot where my window was. Oh, right. So as I said, I was going to show you what one of these stars looks like. So this is an image of a single star, and it's in focus. This is just a very enlarged image of a star, and what you see here in a very short exposure is about a 1/25th of a second exposure.
Oh, 1 second, Mark. We aren't
Yes.
seeing your screen. Will you share with us again?
That's right. I'm sorry. Yeah, I have a lot of windows open and just confused myself. Sorry. Okay, you should be seeing them.
Yes, we do.
Okay. Let's see if I get that. So here, this is in this little window here, what I'm showing you is a very enlarged image of a star that was observed by NESSI. It's a single star, actually, we think. And this is, as I said, an in-focus image, but it's a very short exposure, and it's also very enlarged. What you see here, this kind of model look, is the speckle pattern of the star in the very short exposure. And what NESSI does is take almost a movie-like data, so one image after another, about 25 times per second. So about the same speed as a typical film movie might have been made back in the day. And when you take such a short exposure, you tend to see these nice speckles. And I can advance from one frame to another. And you can see that from one frame to another, the speckle pattern is completely different. So this is essentially, as I said, different parts of the 3.5 meter telescope are imaging the same star, but the light from the star is slightly refracted, and it ends up at a slightly different point when focused on NESSI's camera. And so what I will do now is play this at speed. This is a little bit slower than a true speed, but this is what the speckle image of a single star looks like, imaged through NESSI. And you can see it kind of jumping around. Some of that is where we've actually moved the telescope to help guide or keep the data coming on the camera correctly. Some of them on occasion might be shakes from the wind if this was a windy night. I don't know that it was. So that's what it looks like. When we look at these stars all night, and it's kind of mesmerizing, but this is what we look at all night for observing. So I might actually at this point show you what it looks like when they have two stars together. This may or may not be easy for people to see, but this is actually a binary star. And it's going to be hard, I think, to pick it out for some people if you're not used to looking at it. But what we have here are two speckle patterns, one from one star and one from the other, and they're sort of overlapping. Not completely overlapping, they're offset from one another. And you might be able to tell on certain frames that there are two patterns there that are identical and they're overlapping. They have this might be a good one. So there's kind of a blob here and there's a blob here, and those are the same parts of the speckle pattern from two stars. And this is the power of speckle imaging. We can actually disentangle this mathematically. If we have a bunch of these images, you can kind of see another collection of speckles here, and that kind of lines up with this over here. When you look at a lot of these, you get to be able to see them more easily. I could play this as well. You might kind of tell that there's a double pattern in kind of in this direction as I'm moving from kind of here versus here. And those are the speckle patterns of the two stars, which are comparable brightness. So that's kind of what it looks like. Okay. So I'll go back to my slideshow. Looked at that, and this is kind of a diagram of what NESSI looks like. A diagram on the left and a photograph of NESSI on the right. A photograph taken in a lab. It's a lot easier to see the parts when NESSI's the cover of NESSI has kind of been removed in this photograph, so we can look inside what is essentially kind of a suitcase size box with a bunch of stuff stuck in it. And NESSI is a relatively simple instrument. And I'll kind of go through the diagram on the left. What happens is the light from the telescope is coming in here to the side of NESSI, and it's actually focused somewhere around here, near the edge of the box. And then these lenses in here are imaging where the light is focused up here. It's called collimated light, and we use this kind of completely defocused light in the middle of the instrument as we pass it through the filters particularly. But this light comes in here and it hits a kind of 45-degree piece of glass. And this glass is designed to reflect blue light and to transmit red light. So what happens is the beam hits this glass here, the blue light is reflected, and it's because this is situated at 45 degrees, the blue light is passed in this direction, while the red light continues straight on through the telescope. And what happens is we treat each of these two different beams, a blue beam and a red beam, the same. Each one goes through a filter, a red filter or a blue filter, and each one goes through another set of optics on the other side of the filter. And that will refocus the light out here and over here where the camera's detectors sit. So that's essentially what's happening. We're actually able to simultaneously observe blue light and red light with NESSI. I'll continue on here, I guess. And this is what it looks like inside the box. There's a lot of cables in there. It's kind of interesting because we use a lot of kind of off-the-shelf components like USB controlled things. This is a little different than most instruments, which are made of more custom parts. And these very expensive high-speed cameras are kind of state-of-the-art as well. But other than that, it's a relatively simple instrument. And this is actually the same double star that we were looking at moments ago. Hipparchus 38870 is what it's called. And what we see on the left was one of our 40 millisecond or 400th of a second exposure frames. And that's a good frame because we can kind of see the double star in it of these two speckle patterns. But if we took a longer exposure, and this is equivalent to a 40-second exposure in the middle, you can see that the stars have kind of blurred together. And it would be difficult to tell if it's a binary star in this case. It may be looking a little elongated, but it'd be very hard to say a whole lot about it. So this is what it looks like if you take a traditional image, a long exposure in the same at WIYN here. Now, as I said, we can mathematically figure out what is going on underneath inside of these speckle patterns and kind of reconstruct what the image on the sky would look like. And that's what we see over here on the right. It looks a little funny, but what we're seeing is a bright star, we could call it a primary star. And so on one side or the other, we see a secondary star in this case. Now, you see 3 points there. That's actually an artifact of the mathematical algorithms that we're using to reconstruct the image. They're not perfectly able to distinguish all the time between whether you have a secondary star that lies in one direction relative to the brighter primary star here, or whether it lies in the other direction. And our reconstructed image actually ends up with kind of an ambiguity about this direction of the two stars or their relative orientation. So that's a little funny, but that's what's going on there. If you're familiar with the arc-second scale, this particular binary, these two stars are about 0.38 arc-seconds apart. So they're easily resolved here at WIYN once you do the speckle technique. And at WIYN, the closest kind of binary we might be able to resolve is about 0.05 arc-seconds. Or another way to think about that is the kind of natural seeing at WIYN might be 0.8 arc seconds, maybe 1 arc second on some nights. And that might be about what you get when if you took an image like this. This might, the width of this blurry image here might be about that 0.8 arc seconds or so in resolution. So we can, with speckle imaging, do maybe 15 to 20 times better than in terms of our clearness or our resolution than if we did not use speckle imaging, but just took long exposures. Another way to think about this is imagine these are 2 headlights on a car. If you had 2 headlights on a car, how far away would that car be? And would you be able to see that as 2 headlights using WIYN and using the speckle technique with NESSI? And the answer is you would be able to see a split car headlights about the distance across the continental United States. So that gives you a kind of idea of how good we can do here at WIYN with NESSI. And that's very valuable for us scientifically. So I'm not sure if I can see any questions, but I think there have been more questions coming up.
There have been some questions
Okay.
and comments. Nick has been engaging with us and answering a lot of those questions and helping also to support some of the things that you've been saying and giving us some further insights into, for example, why they were using for some of the components, off-the-shelf components, rather than custom-made components and things like that. So, but we do have a question that just came in from Phil, who asked, does speckled imaging work on extended objects such as galaxies or like planets?
I would say the question is yes, it should work on them, and some people have used NESSI to good effect. The limitation is often that we don't have enough photons because galaxies tend to be they're just too faint to do a lot of things with NESSI. NESSI requires a lot of photons if you're going to do something complex like that. So NESSI speckle imaging has been traditionally limited somewhat to looking at stars or point sources or things that are close to point sources, like maybe asteroids, things like that. But people have attempted some more extended objects with mixed results, I would say. I guess, is that all the questions for now?
Yes, that's perfect. Sorry.
Okay.
Thank you. Yeah.
Sure.
Nick just referenced that that NESSI was kind of came before Alapeke and Zorro at the Gemini observatories, which some of our regular guests may certainly be familiar with Alapeke. So I was just about to drop a few links in the chat for that. So that's why I didn't see. I didn't come back to let you know that was good. So no, you're awesome, and I will chime back in with any more questions, Mark. Thank you.
Okay, sure. Thanks, Jamaica. So you might want to know kind of what comes out of once you have a speckle image, what do you get? Well, it kind of depends on your scientific program, but one of the major uses of NESSI is to either characterize or confirm exoplanets. And NESSI has one rule, and there are probably, when you're studying an exoplanetary system, you're probably combining all kinds of different techniques from different telescopes. And NESSI's role is often to ideally identify the host star as a single star, because that's a much easier thing to interpret if you have a planet orbiting a single star than a planet that might be orbiting one star that's a member of a binary or a triple star system. As I said, when you're observing one of these binary stars or triple stars, you're having light from multiple stars getting into your instrument and confusing everything. If you're trying to look at the radial velocity of the star to measure the mass of the planet, that's very confusing if you have two stars in there, because you're trying to measure the location of spectral lines very carefully. And if there are two sets of spectral lines, that's probably going to wipe out your attempt to measure at least a relatively low mass planet. If you have a transit light curve of an exoplanet, you're probably trying to measure the relative size of an exoplanet versus the size of the star. And that's very confusing if you have light from two stars or three stars in there rather than a single star, because you're getting a blended light curve and you're actually diluting your signal. And you're going to have a tendency to underestimate the size of the planet if you don't account for that second or third star in the system. So kind of one of the products that we get from NESSI is called a contrast curve. And this is what people often want at the end of the day when they get NESSI data. And this is a plot that measures how deeply imaging we are the sky surrounding a star as a function of distance from that star. So you can see along the bottom, this axis, this is the separation from the star. So if our star, our target star, sits at 0 here, at a certain separation, and this is the angle in the sky or distance across our image, this gives us an indication of whether we detect or do not detect any stars nearby. And in this case, this red curve is what people care about, actually. This is eliminating a whole bunch of possible, this looks like a single star. This is eliminating a whole bunch of possible cases where you would have a blended star, because we look there and we only see a single star. So a lot of people will be able to put a probability on there being a second star in there as a very low number. And that's an essential part of confirming whether a star is hosting a planet or not. Or if you think there's a planet there already, whether you're measuring its correct radius or not. And this is a nice cartoon. This was part of the poster that was actually sent around as part of the announcement for this opportunity, for this Zoom session. So on the left, you can kind of see a transiting planet is passing in front of its host star, orbiting. It's blocking a certain amount of light. And if you measure the brightness of that star over the course of time, when the planet passes in front of the star, it's transiting the star, as we say, it's blocking a certain fraction of the light. And that fraction of the light tells you the ratio of the size of the planet to the size of the star. So it's just blocking a certain fraction. If you have a larger planet, it blocks more of the light. Smaller planet, it blocks a smaller fraction of the light. Now, what if you had two stars there, as you see in the middle panel, but you didn't know it? You didn't have a high resolution image yet. Well, in that case, you would, if you looked at the same transit light curve, you see the same amount of dimming. If you had two stars there, that would mean that you would require a larger planet there to produce that same amount of dimming. But if you assume there were only one star there, you would actually underestimate the size of the planet. in the case of if it was actually a binary star. And then you have all kinds of different cases. You might be confused about which two stars, if you knew there were two stars, which of the two stars hosted the planet. So it can be very confusing. As I said, binary stars are not ideal to study in many cases if you're looking for exoplanets or trying to understand their properties in a lot of detail. But potentially with speckle imaging, you might get close and start to understand what types of planets can exist in a binary system. So that's just an example of the kind of science people are doing. So that's the end of the kind of science cases. I did have a few other photos I can share. They're about the observatory in general. But are there questions at this point?
I have a question. This has been really insightful, Mark. I have a question on there's a NESSI triple star system that I was going to ask about, and perhaps you even participated in these observations. And I was just curious if you could tell us a little bit about it. I'll drop the link in the chat here. Oops. And maybe you will you can share your screen and take us there after showing us the images that the other images that you
Did I lose my? Where's my image? So now I'm not used to doing a lot of sharing at Zoom. So my chat.
No worries. You're doing great.
Okay,
I know it. Yeah, so you were talking about the blue light and the red light, and I thought this really does really help us to visualize that really well. And I thought maybe perhaps you could also give us some insights on this triple star system and how NESSI's observations helped with this identification.
Okay, I guess what you're seeing here, and I'm sorry I don't remember all the details about this system, but I can talk in general about this is a triple star somewhere, and I suspect this is very likely a star that was at least a suspected host, maybe a known host of a transiting exoplanet. So as you can see, we in the blue colored image is on taken from NESSI's new blue beam, which is kind of a visual wavelength, 562 nanometers, like what your eye might be seeing. And on the right, this is from NESSI's red beam, which is beyond a redder light than you would see with your eyes. And this looks like another case where we're not actually able to decide the relative orientation of the bright primary star and the two fainter secondary and tertiary stars in the system. This is very likely, just from a probability standpoint, a true triple system, because these stars are actually so close together and relatively comparable in their brightnesses. Just from a statistical standpoint, we would tend to say this is a true triple system. There are various ways to figure that out. One way is to take images a year apart from one another, and if these stars, and they're often nearby stars, if they're moving through the sky, so-called proper motion, fast enough, if you have two stars that are simply co-aligned along the same line of sight but are actually not orbiting one another, you would actually see them start to move apart. But if they're actually orbiting one another, they tend to move through space together. And they would, if you watch a star a year apart, 2 years apart, 3 years apart, and they sit at the same location, and you know how fast they're moving across the sky, that will be one indicator that they're a true triple system. I think another thing you might see here on in the image on the right, you see the third light in here, the faintest one of these stars is rather bright, relatively speaking, in the red, and is maybe not even visible over here in the blue. That's very typical also for a true triple system or a binary system, because of the relative colors of the very low mass stars. They're relatively red stars, and they are also the fainter stars. Just by the color and temperature relationship between a star's mass and its temperature and bright and relative brightness. But I don't recall the exact details of this system here.
No worries. That was perfect, Mark. Thank you for that explanation there. And just in general, once you get the images, the various speckle images together, does it take a lot of processing to get an image like what we're seeing here?
Yes, it can take. We have automated software to do it, but speckle imaging is often, you might compare it to a shoot first and ask questions later technique, where you take the data and you don't know exactly how it's going to turn out until you process it. But that processing is slower than you typically can do while you're observing your targets. So what we do is we take the raw data, we take the data at night, and we only reduce it maybe within the next 24 hours. If we're lucky, we might 24 hours later have reduced it and can look at it. So we don't always know exactly how well we've done, but we have some idea, just kind of based on the conditions and the brightness of the star, how well we might have done. So speckle imaging is an older technique than some others, like what's called adaptive optics. So with speckle imaging, we just take the data in the atmosphere, all the atmospheric effects are in the data, and then we have to analyze that later. With adaptive optics, another technique for getting high resolution images, you're actually having your optics, which deform, or they're able to move. You're actually moving optical surfaces around to compensate for what the atmosphere is doing. And in that case, you can actually instantly get an idea, instantly get these high resolution images. Okay, and there's a question that came in: is this lucky imaging like amateurs use on planets? Speckle imaging is different than lucky imaging. And you might remember, like, this might be a good thing to talk about. You might remember from the image back here, this is kind of the pattern that hits the mirror on a telescope here. You have light areas and dark areas. These are also, you might say, they're good parts of the image and bad parts of the image that are all hitting the mirror at the same time. And in lucky imaging, if you have a smaller telescope than WIYN, what happens is in some of these very short images, and lucky imaging uses relatively short images, you'll have very good conditions. You'll have a good image, good seeing as it's called. You'll have a good sharp images. And then on some other images, you'll have relatively bad conditions. And then lucky imaging, you just look for all maybe the top 10% best images of these very short images, and then you add those together to try to get a very good high resolution image. That doesn't work as well as you get to larger and larger telescopes, because you tend to capture more and more of these different patterns all simultaneously. So you don't have a lot of variation from the very best images to the very worst images. So speckle imaging is better than lucky imaging as you go to larger and larger telescopes, where these effects, the bad and good images, tend to average out on the same exposure too much. So it's a good question.
Yes, Bill, thank you for asking that, because I thought they were, I know lucky imaging is a type of speckle imaging just in general, but I thought they were much more similar than they actually are. So yes,
Well,
thank you for,
very much related, but a little different, yes.
gotcha. Okay, awesome. And so, Mark, I see that we have just about 3 more minutes left in our first session with you. Could you tell us a little bit more about the work that maybe like your research? Does it involve speckle imaging, and when could we hopefully expect to have another session with you?
Okay. My own research has actually been included as part of the queue often. And I'm interested in exoplanets in all different ways. And mostly I'm a team member on different teams who are trying to characterize these exoplanets. And my role is to use NESSI, as I showed you with that contrast curve, to try to ideally find single stars and eliminate the possibility that there's blended light in these systems. And when we do that, then those are the planets that people really like to work on. They can get very accurate estimates of the planet properties. So I'm doing a lot of that. So in terms of the next NESSI session, we can try maybe in September. That's the next scheduled NESSI Q night. I only use NESSI maybe about a week out of each semester, and that's usually broken up into, say, 2 different observing runs on 2 different months. So I think next semester, NESSI will be on the telescope for a few nights in September, and then again a few nights in January. So we can try to see if one of those will work out. And then I didn't actually show you our NESSI GUI, didn't have time, but I can kind of show you what we would be looking at in that case. Where is this? Oh, right. That's funny. I was gonna be able to show you the NESSI control software, but that's not as interesting if we're not actually observing with it. But yeah, maybe in September we can try again.
Well, I certainly look forward to that. I do. Are there any other questions before for Mark or Nick before we wrap up this very first session with Mark from Kitt Peak National Observatory? So, okay, well, with that, Mark, could you maybe drop a link to a recent paper that you have that we can, so we can learn a little bit more about your own research before we see you hopefully in September?
I can try that. Let's see.
Excellent. And we have thank yous, great presentation, comments in the chat. Thank you all so much for being with us. Rob, Vani, Yael, Irene, Phil, Eddie, thank you all for the great questions and for joining us. And Nick, thank you so much for being here and for, again, your wonderful explanations and the engagement and the chat with us. You all look forward to on our Shadow the Scientist website. And if you are in our mailing list, you will certainly get updates on when we'll have our next session with Mark Everett with Speckle Imaging, and our very first session with Nick Scott at the Char Array, which will be coming up shortly. Maybe Nick, as Mark finds a link to share with us to one of his most recent papers, would you like to maybe chat with us quickly about what we can expect in your Char Array session?
Sure. Did we settle on a date for that yet? I'm trying to look through my calendar, but I don't. It's soon.
Looking at
I think August 2nd or so. But yeah, so the Char Array is it's similar to Speckle in that it's interferometry, except instead of catching the light with a single telescope, we use separate telescopes spread out across the mountain. They catch the same light and then bring it together at the camera and combine it there interferometrically, which is the same thing as happening with Speckle, just on a larger scale. And what that allows the Char Array to do is get resolutions, angular resolutions that's equivalent to, from here in LA, being able to see newsprint in New York City. So 3 millimeters from 3,000 miles, if you don't mind mixing units. And I think the night we have scheduled is going to be some engineering. It's going to be a few different tests going on, and I'll give kind of a tour of the array, but it's kind of fascinating stuff. Smaller telescopes than where Mark is, the WIYN. WIYN's a 3.5 meter. The Char telescopes are 6 1-meter telescopes, but they're spread out from 34 to 331 meters across the mountain. So it's a very interesting and very unique facility. There's only a few operating interferometers in the world.
Well, we are certainly looking forward to that, Nick. Thank you so much for that bit of primer to get us ready. And yes, we did settle on August 2nd. So you all will be getting, you'll see it on our website soon. And if you're on our mailing list, you will get the promo there as well. Thank you so much, Nick. And Mark, yes, I see you dropped a link to a paper here, Gliese 12b, a temperate Earth-sized planet at 12 parsecs, discovered with tests and CHIOTS.
Yeah, that's kind of a good example of where NESSI plays a small role in the discovery and characterization. NESSI is looking at this star. It turns out to be a single star, which is good. And they're able to measure the properties of a small planet. So that's very interesting.
Well, I'll be sure that I read this paper before our next session with you. Mark Everett, thank you so much for allowing us to shadow you in this session. And everyone else, we look forward to seeing you in a future Shadow the Scientist session. Thank you so much. Take care. Aloha.
Thank you, Jimmy.
Bye, Mark. Hope the weather gets better for you.
Oh, thank you. We'll try. Thanks, everyone.